Here, the general term of frames and machines refers to the type of structure that is composed of multiple pin-connected members, and each of these members usually is also subject to multiple forces and moments. Therefore, in terms of static equilibrium, frames and machines can be more difficult to analyze than the truss structures that we learned previously. You need to have a very clear understanding of Newton's third law, action and reaction, since we will apply this law frequently during our analysis. And as a general approach, it always helps to start the problem with identifying the two force members in the structure. In this example, we have a compound beam that is made up of two members, AB and BC, which are pinned together at point B. We need to determine the support reactions at point A, a fixed support, and at point C, a roller support. Let's first treat this compound beam as one system and apply the force analysis method that we learned before for rigid body equilibrium and see what happens. So we remove the supports, set up our coordinate system. To complete the free body diagram of this compound beam, we need to note the support reactions. At point A, we have a fixed support, therefore there are three associated support reactions. We have a horizontal force, vertical force, and a moment. All three are drawn according to the assumed positive directions. And at point C, because we have a roller support, there is only one vertical force reaction. Now, before we try to write equilibrium equations so we can solve for the unknowns, let's remind ourselves that we have learned for each two-dimensional rigid body free body diagram, we can only write a maximum of three independent equilibrium equations. But we have four unknowns here. Therefore, we do not have enough equations to solve for all of these four unknowns. So in order to solve this problem, we need to draw separate free body diagrams for members AB and BC. Now the two members are separated, and we need to complete the free body diagram for each one of them. For member AB on the left, again, we have the three support reactions from the fixed support. And at point B, because we have a pin connection, there are two force reactions associated with it, a horizontal one and a vertical one. For member BC on the right, again, we have the vertical force from the roller support. And at point B, we do not need to introduce new support reactions. We again have forces Bx and By, but they must be of opposite directions as the two force reactions we draw for member AB on the left. So why are these forces of the same magnitude but opposite directions? Well, you can consider them as action and reaction. But more accurately, their relations are determined through pin equilibrium of the pin at point B connecting these two members. And I will discuss this a little bit more later. But now we have two completed free body diagrams. For each one of them, we can write three equations. So 3 here and 3 for member BC. So overall, we have 6 equations and we have 6 unknowns. So now we have enough equations to solve for all of our unknowns. It's probably easier to solve for member BC first and then solve for the remaining reactions on member AB. And this completes this problem. But what happens at point B? Now let's analyze the pin that connects these two members. Let's recall what we've learned in the method of joints. For members connected through a pin, if we separate them, these are the forces exerted by the pin to each of these members, and because of Newton's third law, action and reaction, these are the forces exerted by the members to the pin, and these are 4 pairs of forces with the same magnitude and opposite directions, and the pin is in particle equilibrium. And this is similar to our example of the compound beam. Previously, we have already solved for the reactions at point B, and instead of using the horizontal and vertical components, let's replace them using their resultant forces. Once again, these are the forces exerted by the pin to member AB and member BC. And again, because of Newton's third law of action and reaction, these are the forces exerted by the members to the pin, and the pin is in particle equilibrium. And how exactly are these forces exerted on the pin? Well, that depends on the details of the connection. Here is an example of double shear connection. Member AB exerts this 1.53 kN force on the pin, while each of the two leaves from member BC exerts only half of that force on the pin. Or the connection could be single shear, and each of these two members AB and BC exerts the same amount of 1.53 kN force on the pin. This analysis is very important in the design of the connection. We need to consider this when we choose the appropriate material and size for the pin, and this will be discussed in the course Mechanics of Materials. Let's look at this simple example involving a pair of pliers. If we exert a pair of 120 Newton forces on the handles of the pliers, we need to determine the clamping force each lever member exerts on the metal ball at point A, as well as on the joining pin at point B. A quick analysis tells us that the metal ball at point A is a two-force member. Therefore, the forces acting on this ball must be a pair of forces with the same magnitude, same line of action, and opposite direction. And because of action and reaction again, these are the forces exerted by the ball to each lever member. Notice that these are collinear. Therefore, if we treat this pair of pliers as one system, we cannot solve for the force Fa, nor can we solve for the forces at pin B because the forces at pin B are internal to the system. So we must analyze only one member. Let's choose only one lever member and draw its free body diagram. This is the force exerted by the ball to the member, and these are the two force reactions associated with a pin connection. We can write three equilibrium equations, and we have only three unknowns, therefore we can solve for all of them. If we choose the other lever, compared to the previous slide, notice how I draw all the forces in the opposite directions. This is based on my understanding of action and reaction as well as equilibrium. And if you set up the three equilibrium equations and solve for these three unknowns, you should get exactly the same results. And I will leave it to you to do that. Let's look at this example. For this frame structure made up of slender members connected and supported by pins, we need to determine all force components exerted on all four pins at A, B, C, and D. Notice that this is not a simple truss structure that we learned before, and I want you to think for a moment why this is not. If we treat the entire structure as one system and try to solve for the support reactions at point B and C through equilibrium, we will soon realize that we do not have enough equilibrium equations to solve for all of them. Besides, we still need to determine the forces on the pins at point A and point D. So I am going to show a more detailed approach by analyzing each part of this structure individually. In the future, through practice, you might be able to find shortcuts for some problems of this type and save yourself some time. We start with member AB by isolating it. Replace the distributed load by a concentrated force 120 Newton located at 1/3 location from the base, which is 0.4 meter from point A. At point A, because we have a pin connection, there are two force components associated with it. I'm going to call them A BABX, which indicates this is the force exerted by pin A to member AB along the X direction. And AABY, this is the force exerted by pin A to member AB along the Y direction. And at point B, again, we have the two force components, BABX and BABY, represent the forces exerted by pin B to member AB. So now we completed this free body diagram, we can write overall 3 equilibrium equations. We won't be able to solve for all unknowns. However, through the equilibrium force analysis along the X direction, as well as the equilibrium of moments summarized about point A, we can solve for 2 of these 4 unknowns. And from the last equation, the force analysis along the Y direction, we can draw the conclusion that BABY equals to negative AABY. We mark the solved forces on member AB, and then we move on to pin A. These are the 2 forces exerted by member AB to pin A. Notice how I switched the direction because of action and reaction. And these are the 2 new unknowns. These are the forces exerted by member AD to pin A. And from a simple particle equilibrium analysis, this is what we get. Now we move on to member AD, which is subjected to the known 400 Newton vertical force. At point A, we have these 2 forces exerted by pin A to member AD. Notice again, I switched the direction of these 2 forces. And at point D, these are 2 new unknown forces exerted by pin D to member AD. And since here we only have 3 unknowns and we can write 3 equilibrium equations based on this free body diagram, we can solve for all 3 unknowns. And because now we know what AADY is, from the previous step, AADY equals to AABY, therefore that is also solved. And from the very first step, BABY equals to negative AABY, therefore now we also know that BABY equals to positive 200 Newton. We mark the solved forces and move on to member BD, which is a 2-force member. That means that the force exerted by pin D to member BD and the force exerted by pin B to member BD are of the same magnitude, same line of action, and opposite direction. But we do not know what this magnitude is. So we move on to pin D. It is subjected to these 2 forces exerted by member AD. Again, I switched the direction. This is the force exerted by member BD to pin D. And these 2 are new components exerted by member CD to pin D. Remember, each particle free body diagram enables us to solve for maximum of 2 unknowns. But we have 3 unknowns here, therefore we cannot solve for any one of them. So let's leave it for now and move on to member CD. For member CD, these 2 are the forces exerted by pin D to member CD, again action and reaction. And these 2 are new force components exerted by pin C to member CD. Based on this free body diagram, we don't have enough equations to solve for all 4 unknowns. However, from these 2 equations, we can solve for these 2 unknowns. And the third equation, resultant force along the Y direction equals to 0, gives us this relation that CCDY equals to DCDY. Now, since we know now what DCDX is, and notice that this is one of the unknowns from the previous step. So now we can solve for the remaining unknowns from pin D. And we know these 2 now as well. This is what we've got so far. We're almost done. The only things left are the pins at point B and point C. For pin B, these are the forces exerted by member AB and BD that we solved previously, And these two unknown forces are exerted by the actual brackets of the support fixed on the ground to pin B. And we can solve for both of them. And we can do the same thing for pin C. And this completes this problem. And if we treat the entire structure as one system, you can show that the structure is in equilibrium.